Imagine buying a massive, expensive filing cabinet for an office that generates absolutely zero paperwork. That is basically what adding register tokens to a pixel-space diffusion transformer should feel like.
Sure.
On AI Paper Slop today, we are diving into Registers Matter for pixel-space diffusion transformers by researchers at Yandex Research. And here is the 30-second download. Vision transformers, right? They are known to need register tokens to fix these high-norm patch token outliers.
Right, background artifacts.
Exactly. So this paper asks if diffusion transformers or DITs need them too. And the surprising answer, DITs do not naturally have these outliers at all. Their patch norms are completely uniform.
Completely flat.
Yeah. Yet adding register tokens to pixel space DITs dramatically improves generation quality and convergence anyway. The registers artificially create high-norm tokens, acting as, and this is key, norm sinks and global semantic carriers.
Which is fascinating because they smooth out intermediate feature maps, especially at high noise levels.
Right. And the paper culminates in this highly efficient, compact dual-stream architecture that gets you these massive gains with only a 14% parameter bump and zero runtime overhead. So, look, if you are an ML engineer trying to squeeze better generation quality out of your pixel space diffusion models, you need to hear this.
Yeah, you really do. It fundamentally challenges our assumptions about architectural inheritance, because we're seeing this massive shift right now where diffusion models are abandoning convolutional backbones in favor of transformer architectures.
Like training directly in pixel space instead of latent space.
Exactly. And the default assumption in the field has been that, well, as these models become more like VITs, they naturally inherit the exact same flaws. But the internal mechanics of a DIT, as this paper definitively proves, they just operate under entirely different constraints.
Which brings us to the baseline assumption of this whole experiment.
Yeah.
In standard VITs like DynaV2, we know that register tokens were introduced to solve a very specific problem, attention artifacts. The model would hit a low information region of an image, like a blank wall or a clear sky, and suddenly would generate these massive high-norm token outliers that completely hijack the attention maps.
Yeah, the theory in the VIT literature is that the model was sort of repurposing those useless background patches to store global image information, simply because it lacked, dedicated memory slots to do so.
It had nowhere else to put the data.
Exactly. So you append empty register tokens to the sequence, you give the model a dedicated place to store that global context, and the background patches return to a normal distribution. The attention artifacts vanish.
So logically, the Yandex team looks at DITs and figures, hey, we should test if the same background artifacts exist here and if registers fix them. And this is the crazy part. When I was looking through their attention maps for both latent space and pixel space DITs, I couldn't find the artifacts at all. The maps are totally clean.
They are completely clean. It's really striking. When the researchers plotted the token-wise feature norms across the layers of a pixel space DIT or a PDIT, the distribution was entirely uniform.
There are just no high-norm outliers spontaneously emerging in the background patches.
Right.
Which makes my engineering brain say, well, leave it alone. If it ain't broke, why fix it? If the data distribution is perfectly clean, injecting useless empty tokens seems like a fantastic way to just waste compute. I mean, why would you add registers to a model that clearly doesn't have the outlier problem they were invented to solve?
And that is the exact intuition that makes this paper so compelling. Based strictly on the VIT literature, DITs should not benefit from registers at all. It makes no sense. But when the authors actually ran the training with appended learnable register tokens, they saw consistent generation quality improvements across the board.
I want to make sure I'm reading their ImageNet results correctly here, because the jump seems huge to me. Did the FID really drop a full point just from adding blank tokens?
It did, yeah. For a base PDIT at 600 epochs on ImageNet 256 by 256, the baseline without registers sits at an FID of 4.80. You add the registers and it drops to 3.80. And this scaling held true for their large and huge model variants as well. The improvements are undeniable.
Okay, so if the registers aren't absorbing pre-existing outliers to clean up the attention maps, what on earth are they doing once they are injected into the DIT architecture?
Well, this is where it gets really interesting. When the authors plotted the future norms for the model with the registers added, they found that high-norm tokens spontaneously emerge within the registers themselves.
Wait, so the model didn't have outliers before, but the moment you introduce these penalty-free slots into the sequence, the model just exploits them.
Exactly. It artificially creates the outliers it wasn't allowed to have previously.
When you say penalty-free slots, is this about the difference in how the loss is calculated between the two architectures, like between a VT and a DIT?
Yes, exactly. In a vision transformer, typically only a class token participates in the final loss computation. That leaves the image patch tokens largely unconstrained, which is what allows those high-norm outliers to emerge in the background in the first place.
Right.
But in a diffusion transformer, every single patch token is actively constrained by the diffusion loss objective. Every single patch is being penalized if it doesn't correctly predict the noise or the score.
So the image patches are just working too hard. They don't have the luxury of becoming a storage bin for global data because they are strictly accountable to the loss function at every step.
Yes.
But the moment you add registers, which are entirely excluded from the diffusion loss, the model immediately offloads that burden onto them.
Precisely. But the fascinating part is what it actually offloads. The authors use linear probing to analyze the representations inside these register tokens, and they found two completely distinct types of behavior emerging within them.
Right, I saw this in the paper, the dual behavior. Some registers exhibited really low accuracy for predicting the image class, but they had extremely high feature norms.
Yeah.
And then others had high accuracy for classification, but relatively low norms.
So the low accuracy high norm tokens are acting as pure norm sinks. They're just absorbing mathematical magnitude and local variability that doesn't really carry semantic meaning.
Like a sponge.
Exactly, like a sponge. Meanwhile, the high accuracy tokens are acting as global semantic carriers, storing the broad context of the entire image.
It's almost like the model is spontaneously specializing these free tokens into two distinct roles on its own. Some become, like you said, sponges or trash cans, and the norm sinks, just absorbing the mathematical noise, while the others become this executive summary, the semantic carriers holding the global context.
That is a highly accurate way to visualize it. And if you think about the geometry of the representations, this offloading is incredibly liberating for the actual image patches.
Because they don't have to carry all that extra baggage anymore.
Right. By moving the high magnitude trash and the dense executive summary out of the spatial grid, the actual image patch tokens are finally free to form smoother, more spatially structured representations.
Okay, so since we know how they function as norm sinks and semantic carriers, the natural next question is why they work so much better in pixel space specifically. Because the authors did test registers on latent space models like SIFT, right?
They did, yeah.
And while there was a small benefit, the really game-changing improvements were isolated to the pixel space models. Why is that?
To understand that discrepancy, we have to look at a metric called total variation, or TV. Total variation is a mathematical measure of spatial smoothness across a feature map. It basically quantifies the intensity differences between adjacent patch features.
So high TV means your feature map is really noisy and disjointed.
Exactly. And low TV means it's smooth and structurally coherent.
And pixel space is inherently a much noisier, higher dimensional environment than a highly compressed latent space. Like you are dealing with raw, high-frequency pixel data.
Precisely. The intermediate representations in a pixel space DIT naturally exhibit substantially higher total variation than latent space models. There is simply way more noise and spatial disjointedness to manage.
Ah, I see. So when those register tokens act as sponges and absorb that variability, the resulting smoothing effect on the image patches is just far more pronounced in pixel space because there was more noise to begin with.
Exactly. They have a much bigger mess to clean up, so their impact is much more obvious.
The timing of when this smoothing happens is what really caught my eye, though. The smoothing from the registers isn't just distributed equally across the entire diffusion process. It overwhelmingly occurs at high noise levels, specifically when the time step is between 0 and 0.2.
Yes, and this connects directly to the mechanics of flow matching and diffusion trajectories.
How so?
Well, when you are operating in high-dimensional pixel space at the very beginning of the generation, which is the high-noise regime, the model isn't rendering fine textures yet. It is trained to construct the central global structure of the image out of pure static. It is establishing the broad vector field trajectory toward the data manifold.
It's trying to figure out, like, if it's drawing a dog or a truck before it worries about rendering individual pieces of fur or the headlights.
Exactly. And because that early phase is exactly when the model desperately needs a stable global executive summary, the register tokens provide this critical stabilization.
That makes total sense. By smoothing out the intermediate representations and absorbing all that spatial variance during those vital early denoising steps, the model lays down a much more accurate structural foundation.
And that early stability compounds over the rest of the generation process, which is why you see such a massive boost in the final generation quality.
Okay, so we know why they work and when they work. But the ablation study on where to put them completely subverted my expectations.
The layer depth experiment.
Yeah, because in standard VIT architectures, the practice is to inject the register tokens right at layer 0, at the very beginning of the network. But when the Yandex researchers tried injecting registers at layer 0 in the PDIT, it yielded almost zero improvement over the baseline.
The model actively rejected them. It's wild. They tested introducing registers in layers 0 through 11, and then just in the early layers, like 0 through 4, and neither configuration showed any meaningful improvement.
That is so counterintuitive.
Right. The dramatic FID gains only materialized when they withheld the registers entirely and introduced them deeper in the network, specifically in blocks 4 through 11.
Why is layer 0 practically allergic to registers in a DIT? I mean, if the tokens are supposed to act as an executive summary, why wouldn't you want to start summarizing from the very first layer?
Well, the authors propose the semantic structure hypothesis that explains this perfectly. At layer 0, the model isn't really looking at an image yet. It's looking at a bucket of disconnected puzzle pieces. Raw, disjointed pixel patches.
Okay.
The transformer just hasn't had the depth to build any higher-level semantic relationships between those patches yet.
So if you force the register to summarize the image right then, it literally has nothing meaningful to capture. It just memorizes the shapes of random puzzle pieces.
Exactly. It absorbs uninformative, low-level signals. But the critical issue is that because those registers are now part of the sequence, they participate in the attention mechanism for the rest of the network.
Oh, I see. So those garbage signals get propagated forward.
Yes. They act as weak, noisy conditioning. They pollute the attention maps and actively degrade the network's ability to form coherent structures in the later layers.
So by withholding the registers until block 4, you allow the transformer to build up a baseline level of spatial and semantic structure first. So when the registers finally arrive, there is actually a meaningful global context for them to absorb.
Exactly. It highlights just how sensitive these architectures are to the timing of information routing. But what I find even more fascinating is that the authors didn't just restrict their analysis to theoretical models. They looked at massive state-of-the-art architectures to see if this phenomenon was already happening.
The accidental registers finding.
Yes.
This blew my mind. They analyzed the GT architecture just image transformers, which doesn't use explicit register tokens at all.
Right.
Instead, it relies on in-context class conditioning. You append tokens that tell the model what class to generate.
Right.
But when the Yandex team ran their linear probing analysis on those class tokens, they realized the tokens were moonlighting.
They were functioning exactly like registers. Despite being explicitly programmed to condition the model on a specific class, some of these tokens just abandoned that job entirely. They developed massive feature norms and became norm sinks.
And others started encoding broad global information about the image rather than just the specific class category they were intended to represent.
Exactly. And it isn't just academic architectures either. They brought in massive open source models like Stable Diffusion 3.5 Large and FLUX.
Right, because these models use auxiliary text token sequences from the user's prompt to guide the image generation.
Yes. And even though they were never trained with explicit registers, the models are hacking their own architectures. In SD 3.5, the researchers demonstrated that high norm outliers predominantly emerge within the text token sequence, which beautifully keeps the actual image token norms uniform.
So the model is utilizing the user's text prompt tokens as a functional trash can for mathematical magnitude.
Essentially, yes. It inherently wants to stabilize its own spatial representations, and it is opportunistic enough to hijack whatever free parameter real estate you provide to create those norm sinks.
The fact that a token meant to represent a word from your prompt can simultaneously absorb massive structural noise without breaking the text conditioning is just a massive testament to the flexibility of the attention mechanism.
It really is. It's incredibly robust.
But if you're an engineer listening to this and mapping out the architecture in your head, you might be thinking, wait, if these tokens are behaving fundamentally differently, like one is a mathematical garbage can and the other is a delicate image patch, feeding them through the exact same computational pathways seems like a terrible idea.
And you'd be exactly right. We absolutely need to process registers differently from patched tokens.
Right, so the naive engineering solution is a full dual-stream architecture. You duplicate every component of the transformer block, giving the image patches one set of weights and the registers another.
But the authors highlight that this is a complete disaster for parameter efficiency. If you blindly duplicate a 131 million parameter base model, you suddenly balloon to 230 million parameters.
Yeah, that scales terribly for production models.
Exactly. So how do we separate these completely different token representations without doubling the size of the model?
Right. The paper introduces a compact dual-stream design. Let's break down the mechanics of this. It's such an elegant fix. What components actually require separate weights, and what can be safely shared?
Well, they started with the attention mechanism. The query, key, and value projections, the QKV matrices, contain a massive percentage of a transformer's parameters. The authors discovered that the base QKV matrices can actually be shared across all tokens.
Okay, but how do they give the registers the distinct processing they need?
They simply applied a very lightweight LoRa array, a low-rank adaptation, exclusively to the register representations before they enter the attention computation.
Oh, that is incredibly efficient. Instead of duplicating the massive rank matrices, LoRa allows the model to subtly adapt how the registers query the sequence and what values they output, utilizing only a tiny fraction of the parameters.
Exactly. So attention is largely shared.
Okay, so what components get completely split?
The normalizations and the multi-layer perceptrons, the MLPs, they completely split the RMS norm. Normalization parameters are relatively tiny, so giving the registers their own normalization costs almost nothing in terms of parameter count.
But it is mathematically crucial because, as we established earlier, the registers have vastly different magnitudes compared to the image patches. You absolutely do not want the massive magnitude of a norm sync token skewing the variance statistics for the image patches during normalization.
Correct. You have to isolate them. They also split the adaptive layer norm, the ADALN, by using a shared base but applying a separate LoRa branch specifically for the registers.
Got it.
Finally, and this is a vital detail, they address the SWIGLU MLP. The hidden layer mapping inside an MLP is very parameter heavy. So they shared the hidden latent computation, the linear projection, and the gating, but they used completely separate output linear projections back to the residual stream for the register tokens and the patch tokens.
So it is essentially a surgical uncoupling. You share the heavy lifting of the attention and the hidden MLP dimensions, but you give the model separate pathways to output and normalize the features.
Yes, exactly.
And the empirical results of this architecture are phenomenal. For a baseline single-stream GTB16 model on ImageNet 256 by 256, the FID is 3.71. Swap that to the compact dual-stream architecture, and the FID drops to 3.41.
And you achieve that massive jump in generation quality with only a roughly 14% increase in parameters going from 131 million to 149 million.
That's a huge return on investment.
It really is. And critically, because the architectural splits are so targeted, the runtime overhead is completely negligible. The GFLOPs, the actual computational cost during inference, remain absolutely identical at 23.8.
So you are getting a substantially cleaner, more structurally coherent generation, basically for free at runtime, simply by intelligently organizing how the model routes its internal noise.
Exactly.
It is a total paradigm shift. Registers aren't just bandages for broken attention maps anymore. They are active, vital organizational tools for managing the extreme noise and information density inherent in pixel space diffusion. You are literally giving the model a pressure valve for its own mathematical chaos.
It is brilliant engineering, honestly. But it leaves us with a highly provocative thought to consider. Well, we just saw empirical proof that text tokens and class conditioning tokens are currently acting as accidental registers, soaping up massive mathematical outliers just to keep the model stable.
Right.
So what other tokens in our massive trillion-parameter multimodal models are secretly performing functional structural roles that are completely unrelated to their intended semantic purpose?
Oh, wow. Are we actually the architects of these models, or are we just throwing raw materials at a black box and relying on the model to hack its own tokens to survive its own architecture?
It's definitely something to think about.
It really is. Something to keep in mind the next time you append a prompt to a diffusion model. You can find all the exact mathematical implementations and ablation studies in the Yandex research paper, Registers Matter for Pixel Space Diffusion Transformers.